Kia ora and welcome to video 10 in the series Delightful Differentiation. Today's problem is a nice short one, so let's get straight stuck into it. We have a product of n functions and we want to find its derivative. How do we do that? Find a formula for differentiating the product of n functions.
So this problem is quite neat. I wanted to include it in the series because of a conversation I had a few years ago with a colleague and friend, Dr. Snedden, who's out at St. Kentigern College. Shout out to him. And the conversation went something along the lines of that the product and quotient rule are overrated and they get far too much airtime in a calculus classroom. So the product rule that you've learned is that when you differentiate two functions, say f times g, and we differentiate, we get f dash g plus g dash f. Now, this can go to three functions. If you've got f times g times h, and you differentiate it, turns out it's f dash gh plus g dash fh plus h dash fg. And you can prove that quite easily because you just pair up two of the functions and you treat that as a single function. So f times g is like the first part, and when we want to differentiate something times another function, we go fg and diff, then times by h, and then h dash and times by fg, and then we just apply the product rule a second time, f dash g plus g dash f, which is this bit in here, all times by h plus h dash fg, and we get that equation that I'd memorized earlier. But yeah, talking to my friend Jamie, he was saying, like, when we use logs to differentiate something, we turn products into sums, and we can turn quotients into differences, and that means we can use easier properties of differentiation, like if we want to diff two functions that are added together, we just individually differentiate. We don't need a formula. So for this one, if we want to find the derivative of a product of n functions, so y is equal to f1x times f2x times all the way up to some function fn of x. If we log both sides, and specifically using the log function that's base e, the natural log, because we know how to differentiate that, we can log all of the stuff there. I'm being a bit lazy. And when we log a product, we can turn it into the sum of logs. So we end up getting ln of f1 of x plus ln of f2 of x, all the way up to ln of fn of x. Okay, now implicitly differentiating, once we've logged both sides, differentiating the left, it's log of y. So we know that when we've got log of x, it's 1 over x. But when it's log of something, it differentiates to 1 over something times the derivative of the something, right? That's chain rule. So in this case, we're going to get 1 over y, which is 1 over the something, times the derivative of the something, which so happens to be dy dx. On the right-hand side, log of f1 of x. Well, that's log of stuff, or log of something, which differentiates to 1 over that something times the something differentiated. So we get 1 over f1 of x multiplied by the derivative of f1, which I'm just going to write as f1 dash because I'm going to be a bit lazy here. The next one is 1 over, actually I'm going to consistently use that notation because I can't be bothered writing the brackets out every time. So it's going to 1 over f1 times f1 dash plus 1 over f2 times f2 dash plus all the way up to 1 over fn times fn dash. And lastly, we wanted dy dx, the expression for the derivative of this function, which was a product of n functions. So I just need to move the y up to the top of the right hand side. So it's y multiplied by f1 dash over f1 plus f2 dash over f2 plus fn dash over fn. And of course y was just the thing we started off with, so if I wanted to then substitute that back in, I could just write f1 times f2 times all the way up to fn times the same thing again. Should really learn how to use the copy function on this. I mean, that simplifies because, as you can see there, the denominator of the first term's f1, which would knock off that f1, and then the denominator of the next one was f2, which would knock off that f2. So we'd end up with, just to make a point here, f2 times all the way up to fn times f1 dash for the first term. The next term there'd be no f2, so we'd have f1 times f3 all the way up to fn. This is so unnecessary, but times f2 dash. And then the last term, the fn's would cancel, so we'd have f1 times f2 all the way up to fn minus 1 times fn dash. And the reason I did that is I wanted to show you the parallel to the stuff we started with if we had three functions. Okay, so if we have three functions, the first one gets differentiated and multiplied by the other functions. The second one gets differentiated and multiplied by the other functions, excluding f2. The third one gets differentiated and multiplied by all the other functions, excluding f3. So actually the product rule that we had earlier does work in general if we had four functions. And I got asked this the other day in my class, so I just thought I'd tack this onto the end of the video. I'm not meaning that I is the square root of -1 there, but if we wanted to diff that, okay, we need to diff one of them and times by the others, then diff the next one and times by the others, and diff the third one and times by the others, forgetting what letters I'd actually used, and then diff the last one and times by the others. And that is the product rule for four functions.